and we start off with this thing. The very first thing is we're going to define deformation. This is how we define deformation. So basically we are deforming an object. The shape changes, the size changes, and thereby we can have different forms of deformation. It could be compress, it could be stretch, it could be a twist, twisting the object, could be shear, could be bending, could be bulking. So it has different forms, and we can note down a few of them. Let's move on to the next thing, extension. So extension, we have defined it already. Change in length upon the influence of a force. Let's take a look at some of the diagrams. We have the first one. This is what a spring looks like. So initially, let's say the length of the spring is 10 centimeters. From this point to this point, the length of the spring is 10 centimeter. You can call it original length, L0. And what we do afterwards is we connect a load with the spring, and thereby the spring stretches, it extends, and thereby it has the extension. So once you connect the load with the spring, it will look something like this. Now the total length of the spring from here all the way till here, once you added a load with the spring, you can call this length as new length, L sub n, and the change in the two lengths would correspond to extension. So the change between these two would be called as extension, and thereby we can also write down a mathematical expression from this thing. It would be extension equals L sub n minus L0, new length minus original length. Extension is also sometimes also represented by x, so you can represent by x as well, and mostly it's in the units of millimeters or centimeters, sometimes in millimeters, sometimes in centimeter. And this is the next one, and after that you can just note it down on your workbook. Okay, so let's move on to the next thing, which is the Hooke's law. So before we move on to the Hooke's law, we had to explain some of the key terms, for example the deforming force and the extension and all that, and only then we can explain Hooke's law. Directly proportional is directly proportional to the extension, and the last part of it, within the limit of proportionality. So this is the way you memorize the definition. You memorize it in three parts. Okay, the force applied on an object is directly proportional to the extension, and terms and conditions applied, this is the condition that must be met for the Hooke's law to be applicable. And what do we do? Since the force is represented by F and the extension, let's say we are representing the extension by X. So the first thing, directly from the definition of Hooke's law, we can mathematically express the same thing like this. Force is directly proportional to the extension. Now if I want to get rid of the proportionality sign, I want to convert it into an equation, I need to insert a constant. So the constant in that case is equals x as it is, and the constant in that case is k, small k. And if I rearrange for the value of k, k would equal F over x. Now we are sure about the force. F is the deforming force, x is the extension, and k in this case, which is a constant, is called as spring constant, and the units of k would be Newton per meter, and you can convert it into SI base units as well, and Newton would correspond to kg ms minus 2 into m minus 1, and x, once again I can write x here represents extension. Now the next question is, what does the spring constant of an object tell us, or what information about an object do we get from its spring constant? So let's say I have two springs. One of the spring looks something like this, and the spring constant for that is, let's say 1000, let's 1500, let's say 1500 Newton. Let's go with millimeter per millimeter. Okay, let's be more realistic. You can't have an extension of 1 meters in a normal case for a spring. And I have another spring at the same time, but for that spring, the spring constant is 500 Newton per millimeter. Okay, so let's call it the spring X, and this is the spring Y. Now the question is, since we know the spring constants of these two springs, what information do we get to know, or do we get about the springs because of their spring constants? Let's say if the spring constant is higher, would that correspond to a stiff spring, or the other way, which is not a very stiff, more of a, what do we call that, soft spring? Yes. So higher spring constant would correspond to a stiff spring or a soft spring. Okay, so let me answer that question. The spring constant represented by K, and let's say for the spring X, we can write K sub X. So K sub X is 1500 Newton per millimeter. The unit itself is telling you something. This value itself is telling you something. It means for a change, for an extension, in order to produce an extension of 1 millimeter, or to extend a spring by 1 millimeter, how much force is needed? 1500. We need 1500 Newton just for the extension of 1 millimeter. I mean, this is what the unit tells us. This is what the value plus the unit tells us. Now for the other spring, for which the spring constant is K sub Y, and that was mathematically 500 Newton per millimeter. Now what do we get from here? It means to extend the spring, to extend the same spring, the other spring by 1 millimeter, we need merely 500 Newton. We just need a force of 500 Newton in order to produce an extension of 1 millimeter. Now let me ask you the same question again. Which one of these two springs is easier to extend? Which one of these two springs is easier to extend? Easier means by applying less force. The second one, the last one, and matter of fact, mathematically you can say it is 3 times easier to extend the spring Y. So spring Y is easy to extend, and thereby we can say it would be a soft spring. And likewise, the spring X was hard to extend, and we can conclude that it would be a stiff spring. Now the bottom line is, the bigger the value of K, the larger the spring constant, the harder or the stiffer the spring is. So just by comparing the spring constants of two springs, we can safely answer which one is hard and which one is soft comparatively. Now let's move on to the next thing. So I'm going to draw graphs for Hooke's law, and in the first case, I'm not going to cross the limit of proportionality. So if I'm not crossing the limit of proportionality, it means that these two quantities, force and extension, should be directly proportional to each other. But what I'm doing is I'm just changing the axis. So for the first one, I'm representing force on x-axis and extension on y-axis. But in the second one, I'm going to reverse the axis and x over here. And I'm going to represent two springs, the graph for two springs. So for the first one, the graph looks something like this. And for the second spring, the graph looks something like this. Now I'm going to draw these once again, but for the other one. So for the first spring, it looks something like this. And then for the second one, it looks something like this. Or you can call it the other way around as well. So let's say this is a spring X, and this is a spring Y. Likewise, this is spring X, and this is the spring Y. And you can safely say I have not crossed the limit of proportionality. Therefore, the graphs are a straight line. There's no bending in the graph, at least till now. Now the big question is, if I compare the spring X with the spring Y, which one spring would be softer? First question, which one of these two springs would be softer? And then the follow-up question would be, which should be pretty easy if you answer the first one, which spring has less spring constant? So if I compare the graph of spring X and spring Y, the first follow-up question is which one of these two springs is softer? Ramin. Let's consider the second one. Now in this case, I have the same question. If I compare the spring X and spring Y, which one of these two spring is softer? And the reason being, it is closer to the extension X. Thereby, Y is softer, and the spring constant of the spring Y would be comparatively less. And likewise, for the first graph, the spring constant of the spring X would be comparatively smaller than the spring constant of the spring Y. So this is the information that we can get from the graph about the spring constant. You can note down this pointer. The graph that is closer to extension axis has lesser spring constant, hence softer. Alright, so like I have explained already, the Hooke's law breaks down at limit of proportionality. But as soon as you cross the limit of proportionality, the Hooke's law breaks down. So let us first define the limit of proportionality. I think I gotta refresh for a minute. Here we have, let us define this limit of proportionality. So in simple words, the limit of proportionality is defined as point till which force is directly proportional to extension. So we get a straight line up till that point. You can phrase it in those terms as well. The point till which the graph between force and extension is a straight line is directly proportional to extension. Now, as soon as you cross the LOP, the limit of proportionality, what happens beyond it, that the force and extension are no longer proportional, hence the value of K changes, the spring constant changes. So beyond the limit of proportionality, the spring constant changes. And when I say the word changes, it could increase or decrease as well. But what happens is, as soon as you reach the limit of proportionality, after that, the spring constant decreases. Hence, the spring becomes easier to deform. It becomes easier to deform the spring. Beyond LOP, spring constant decreases, and it becomes easier to deform the spring. So if I draw the graph, and if I place, let's say, force, let's do the other way around. I'm going to place extension on y-axis, and let's say in centimeters, and the force in newtons on x-axis. So it will start off with a straight line, obviously, because force and extension, they are directly proportional to each other. And when two quantities are directly proportional to each other, you have to be careful with this thing. First of all, the graph should be a straight line, plus there's another property of the graph that represents two quantities being directly proportional to each other. One of them is the graph is a straight line. Can you tell me the other one? Exactly. It must be passing through the origin. So for the first one, you see it is exactly passing through the origin, and up till a certain point it would be a straight line, and after that the spring constant has to decrease. So it means the line has to bend, and if the spring constant is being decreased, it means the spring is becoming easier to extend, and hence the line would curve towards extension axis. So we'll show a slight curve towards the extension axis. Now this point over here is your LOP, limit of proportionality. Now if they reverse the axis, then in that case the bending would be towards the x-axis. Okay, so the rule of thumb is the bending of the graph has to be towards extension axis. Whatever side is the extension axis, you have to bend the graph in that direction. So it may not necessarily be towards x-axis or towards y-axis. Now you must have studied a graph something like this as well. Okay, so let's say here we have a graph that looks something like this. Let's say it looks something like this. Now the question is, we studied this thing already, that force and extension are directly proportional to each other. And if they are directly proportional to each other, then the graph has to be a straight line. The second one, it is indeed a straight line. The graph is a straight line. But the second property was that the graph has to be passing through, the line has to be passing through the origin. So this one is not going through the origin. So this cannot be the graph of force with respect to extension. So the extension would be 0. And I'm going to draw another graph over here. You can just draw the axis over here. And I'm going to, let's say I'm going to draw force. I'm going to label force on y-axis, and I'm going to draw the shape of the graph that looks something like this. Now the question is, in this graph, I cannot label extension on x-axis, because if the force is 0, for example, at this point the force is 0, there is still some extension on this graph. So this cannot be the graph of force against extension. Now the question is, in the same chapter, you would have studied a graph something like this. Can anyone tell me what graph would that be? If it is not the graph of force against extension, then it is the graph of force against what physical quantity? And would be related to these, the extension and the length and all, not from a different chapter, would be related to these quantities. So it is the graph of force, cannot be the graph of force against extension, because it is not passing through the origin. Even if the force is 0, there is still some value on the x-axis. So it is a graph for what physical quantity? This is a question. I'm going to write down some of the options here. One of them is extension. If you still believe it could be extension, you can still pick extension from here. One of them would be the total length of the spring in centimeters, and one of them could be original length in centimeters. So the second one represents total length, the first one represents extension, and the third one represents original length in centimeters. So what do we label here on x-axis? This is the first hint. Would be the total length, because first of all, extension can't be there. So extension is straight away into the trash can. Extension cannot be there. And okay, but let me ask you a question. Why do you pick total length instead of L0, which is the original length? So why do you pick total length between these two? For the extension, before there was a force, there was a deforming force. At this point, there was some length of the spring, which is represented by L0. So whatever the length is up till this point, let's say the length was 2 centimeter. So we can safely say L0 equals to 2 centimeter. But the problem is, if I try to plot L0 on x-axis, it has to be first of all total length. It cannot be original length. It has to be total length. If the graph were of the original length against force, L0, let's say in centimeters, and here you have force in newtons, the thing is, the original length never changes. The original length of the spring, no matter if whatever force you apply, original length means the force that was there, the length that was there without any force. So L0 is not going to change at all, and the graph will look something like this, like a vertical line, because L0 can never change. It does not depend on the force. It is the total length that depends on the force, because total length compensates for the force, it compensates for the extension. So if it were the graph of original length against force, it would look something like this, and the graph of total length against force will look something like this, and finally the graph of force against extension will look something like this. Alright, so today we'll continue with the topic of elastic deformation, and we'll try to wind up the most important part, that has the graphical understanding of elastic against the plastic nature of the spring. So we need to start off with this thing, which is, yes, elastic limit. So let me write down the definition. So the thing is, in O-level physics or in IGCSE, but you're done with you have done O levels, for example. So in O-level physics, these two things are treated exactly the same. आपकी जो limit of proportionality थी और elastic limit, these two words were used interchangeably. The syllabus does not demand us to know the difference between these two in O-level physics. But here we consider and we study these two things separately. First, we have the limit of proportionality, which is a limit till which the Hooke's law is applicable. If I draw the graph of it, and I'm going to label, for example, force on y-axis and this the extension or the displacement of the spring on x-axis. And this is a general conventional way of representing extension against force. Extension on x-axis and force on y-axis. The graph will look something like this. The shape, it will look something like this. And beyond this point, the graph is no longer a straight line. It curves, and well, it curves towards the extension axis. So the first point, the point till you have a straight line, is called limit of proportionality, represented by, let's say, represented by P. And the other point at a certain stage would be elastic limit. Let's represent that point by E.